Okay, let's take a look at a few examples where we will solve a circuit using nodal analysis. The first circuit is a circuit that has a voltage source, current source, and a resistor network. So let's start. First thing we should do is define our reference node. So in this circuit, let's call this place the reference node. So that's ground, 0 volts. Since we have a 10 volt source, the opposite end of the 10 volt source is going to be at 10 volts. Now, our goal is to find the voltage at node P and the voltage at node Q. So for P, the voltage turns out to be trivial because there's no element between the 10 volt node and P. So Vp is equal to 10 volts. So that's trivial. For Q, let's look at Kirchoff's current law at this particular node. So we have one current, we call it I1, going into that node. We have another current, 4 amps, coming into that node, and let's say we have a current I2 going out of that node. So in this case, if we analyze node Q, we have I1 plus 4 amp is equal to current going out of that node, I2, and this comes from Kirchoff's current law. Okay. Now I1 using Ohm's law is V over IR. V equals IR, so I1 is going to be equal to Vp minus Vq divided by the resistance 2 plus 4. I2 is Vq over 1. Okay, so now if I solve this, I get Vp is 10 minus Vq plus 8, this whole thing divided by 2 is equal to Vq. So now let's multiply 2 on both sides, so we get 10 minus Vq plus 8 is equals to Vq. Now let's solve this. Let's take Vq all to one side, so we have 18 is equals to Vq plus Vq. Therefore 3 Vq is equal to 18, which means Vq is equal to 18 divided by 3, 6 volts. So we have node P 10 volts, our node Q is at 6 volts. This was an easy example. Okay, so let's do one more example. So here's another example. In this case, we have similar looking resistor network, except instead of the voltage source, we have a current source, but the analysis is identical. So let's start by selecting a reference voltage node. Now for this, let's start by analyzing node P. At node P, the current coming in is equal to the current going out. Okay, so we have the current coming into the node is 1 amp. Current going out is equals Vp minus Vq divided by 6 plus Vp divided by 2. So let's simplify this, and we get 1 is equal to Vp minus Vq plus 3 Vp. So let's multiply both sides by 6, and I end up with 6 is equals to 4 Vp minus Vq. Okay, we'll call this expression 1. Okay, now let's analyze node Q. Node Q, we have, again, current coming into this node is equal to current going out of this node. So Vp minus Vq divided by 6 equals 4 amp plus Vq over 7. Now what we can do is replace Vq, substitute Vq into this expression. So what we get is Vp minus Vq is equal to 4 Vp plus 6. 4 Vp minus 6. Right? So Vq is equal to 4 Vp minus 6. So we can substitute this expression here. So 4 Vp minus 6 divided by 6. So the negative sign change that. 4 plus this to the same thing here. Okay. Now if we simplify this, we get minus 3 Vp plus 6 divided by 6 is equal to 28 plus 4 Vp minus 6 divided by 7. So this leads me to multiply this side by 7, this side by 6. So I get minus 7 times 3, 21 Vp plus 7, 6, 42 equals 28 times 6, which is 168, 8 plus 24 Vp minus 36. Now let's group all the Vp's on one side. So I have minus 21, 24 on this side. So if I bring Vp to the right hand side, I get 45 Vp. And let's bring all the numbers to the left hand side. So I have 42 minus 168 plus 36. This gives me a total of this is minus 90. Therefore Vp equals minus 2 volts. So the voltage at node P is minus 2 volts. Now for Q, we basically substitute the value of Vp here. So we get from here 6 equals 4 times minus 2 is minus 8 minus Vq. Therefore Vq equals minus 14 volts. So we have minus 14 volts for node Q and minus 2 volts for node P.